Welcome to Chapter 4. In this video, we will learn about chemical reactions and what stoichiometry is. This is the first video of Chapter 4. First, let's go over all of the parts to a chemical reaction. Across the top, we have the symbols representing the molecules that are participating in the reaction. These space-filling models of each molecule helps us visualize each atom that is present. On the left-hand side, we have the reactants. These are the molecules that will react together by breaking their own bonds and reforming into new molecules, becoming the products, which are always shown on the right-hand side of the reaction arrow. So in this reaction, our hydrogen, the four hydrogens in the molecule of CH4 will break apart from the carbon, and the two oxygens will break apart from each other, and then they reform. Some of the oxygens will form with a carbon, two of them will form with a carbon, and then the other two oxygens will each form a molecule with two of the hydrogens, making water molecules. The letters in parentheses show what state of matter each compound is. A G means a gaseous phase, L is liquid, S is solid, and AQ is aqueous. If you remember from Chapter 3, when we learned that ionic bonds dissolve in water to break apart into ions, which is called dissociating, that is what aqueous means, dissolved in water. The chemical reaction often doesn't show the water molecules in the reaction as either a reactant or a product, but AQ means there are water molecules in the reaction somewhere or in your solution sample. In this example, each molecule is in the gaseous state, but we can have any combinations of any of the different states of matter in a chemical reaction. The numbers in front of the molecules are the coefficients. Just like in math, if there isn't a coefficient, that means the coefficient is a 1. We have 1 CH4 in the first molecule here because there's no coefficient. That means the 1 is just implied. We've got one molecule of CH4. This 2 means we have 2 of what comes after. We have 2 O2 molecules. On the product side, we have one CO2 molecule, and then we have 2 H2O molecules. That means we have a total of 4 hydrogens and 2 oxygens that is part of the water molecules here. The little numbers after an element in the molecule are subscripts, and we should be very familiar with these already. The 4 here means that we have 4 hydrogen atoms chemically bonded to one carbon atom in this molecule. This 2 means that we have 2 oxygen atoms chemically bonded together to make an O2 molecule. Again, we have reactants on the left-hand side and products on the right-hand side. The difference between subscripts and coefficients is very important. A 2 out in front is a coefficient. 2 H2O molecules looks like this, and it is very different than if we were to move that 2 out to the back behind the oxygen. This would mean you have one molecule of H2O2, which is hydrogen peroxide, and that is very different than water. We're going to start by balancing this chemical reaction. Here are the 4 steps to balancing a reaction, and we will go over them one by one as we balance our example reaction. Here's step 1. We're going to count the number of atoms of each element on both sides of the product and the reactant side. So we have hydrogen and we have oxygen in this chemical reaction. I like putting both of the elements, or all of the elements that are listed in the chemical reaction, in the middle right underneath our reaction arrow. Now I can count on the left-hand side and the right-hand side. This means I have a total of 2 hydrogen atoms on the left-hand side. This means I also have 2 hydrogen atoms on the right-hand side. This means I have 2 oxygen atoms on the left-hand side. And over here, I've got 1 oxygen atom on the right-hand side. So here I have counted, and I can tell now which atom is unbalanced, which is step 2, determining which atoms are not balanced. We know the oxygen atoms are not balanced. Step 3, balance 1 atom at a time using coefficients. The second sentence to step 3 doesn't apply to this chemical reaction, but we'll get to it in a later example. So, as you can see, if we just added a 2 subscript right here, now the atoms would be balanced. But that is wrong. We cannot change the subscripts when we are trying to balance, because now this chemical reaction is forming H2O2 or hydrogen peroxide, not forming water. So we cannot change subscripts. The only thing we can do is change coefficients. As of right now, each of these molecules have a 1 in front of them. But if we were to change and put a 2 right out in front, so that this chemical reaction produces 2 water molecules, you can now see that we have a total of 2 oxygen atoms on each side of the arrow. We have, so far, this, and before we had added the coefficient 2, we had only 1 oxygen atom. Now that we have 2 water molecules on the right-hand side, that gives us a total of, we'll cross out the 1 and write a 2 oxygen atoms on the right-hand side. We still have 2 oxygen atoms on the left-hand side, so oxygen is balanced. But in doing so, we have now unbalanced our hydrogens, because this means we now have a total of 4 hydrogen atoms on the right-hand side. So if we were to add a coefficient 2 on this side for the H2 molecule, we now have 4 hydrogens on both sides of the reaction. Step 4 says, at the very end, repeat step 1 to make sure mass has been conserved. So we need to count if we have our 2 and a 2 here as we had balanced it. We now have 4 hydrogen atoms on each side of the chemical reaction, and we have 2 oxygen atoms. Therefore, mass has been conserved. Remember, each atom has a small amount of mass, so we cannot destroy or create new mass or new atoms in a chemical reaction. Here's a great way to visualize what is happening. We need 2 H2 molecules to react with 1 molecule of O2, and this produces 2 water molecules. This reaction will always happen this way. You can't produce just 1 water molecule with hydrogen and oxygen, or H2 and O2. So again, subscripts are very different than coefficients. 2 water molecules is very different than H2O2. So I have a funny little story here to help you remember this. Do not change subscripts in a molecular formula when you are trying to balance a chemical reaction. If you do change the subscripts, then this means that you will be killing a bunny. And here's the story. 2 bunnies who are friends decide to meet up and catch up over some drinks. The first bunny says, "Can I have some H2O?" The second bunny wants to be like the first bunny and says, "Can I have some H2O too?" The waiter takes their orders and comes back with their drinks. The bunnies say thank you, and they begin drinking, and everything seems to be going well until things are not going quite so well for the second bunny, and they get worse. So, the moral of the story, instead of saying, "Can I have some H2O too?" the second bunny should have said, "Make that 2 H2Os, please." He should have changed his coefficient on the water molecule instead of changing the subscript. Because in fact, the second bunny ordered hydrogen peroxide, which is very not good to drink. So let's say it again. 2 H2O molecules is very different than a hydrogen peroxide molecule. Do not change the subscripts when balancing a chemical reaction. You can only change the coefficients. Mass is conserved in this picture. If you remember, the law of conservation of matter means that no atoms or no mass can be destroyed or created in a chemical reaction, only changed. If you look at this reaction before the reaction has happened, you can count that we have 2, 4, 6, 8, 10, a total of 12 oxygen atoms. On the right-hand side, we should still have 12 oxygen atoms. 2, 4, 6, 7, 8, 9, 10, 11, 12. We have now 12 oxygen atoms on both sides of the reaction. If you were to count each of the different colors of atoms, which represent the different types of atoms, then you would see that we have the same number on both sides. You cannot destroy an atom or create a new atom with just a simple chemical reaction. That is what we are doing when we are balancing a chemical reaction. Let's do a couple more examples. We are going to balance this chemical reaction by changing the coefficients. Let's write out all of the elements that we have in this chemical reaction underneath the arrow. We have aluminum, we have nickel, and we have bromine. We're going to count up. We have so far 1 aluminum on the left-hand side and 1 aluminum on the right-hand side. We have 1 nickel on the left-hand side and 1 nickel on the right-hand side. We have 2 bromines on the left-hand side and 3 bromines on the right-hand side. Step 2 says determine which atoms are unbalanced. That is, our bromine atoms are not balanced. Step 3 says to balance the chemical reaction by changing coefficients. As you can see, if we were to change, say, this 3 to a 2, or if we were to change this 2 to a 3, you could see that we would then be balanced. But that would be a completely different chemical reaction, or a completely different chemical molecule that we'd be working with. In fact, neither of those exist. But even if they did exist, they would have different properties, and that is not what we're dealing with in this chemical reaction. So we cannot change the subscripts. We can only change the coefficients. If you look and see that on the left-hand side, bromine comes in a ratio of 2, and on the right-hand side, bromine comes in a ratio of 3, the least common multiple between 2 and 3 is 6. So we're going to try to get each side to have 6 bromines. We change this coefficient to a 3, and now we can recount. We have 3 times 2, and we have 6 bromine atoms on the left-hand side. We've also changed our nickel, so now the nickel is out of balance, but we can fix that later. On the right-hand side, if we were to place a 2 coefficient here, we now have 2 times 3 as 6 bromine atoms on the right-hand side as well. Again, we have unbalanced our aluminum, but again, we can easily fix that. If we put a 3 as this coefficient and a 2 as this coefficient, we now have 2 aluminum on each side, 3 nickel on each side, and 6 bromine on each side. This chemical reaction is now balanced. Let's do another example. We have carbon, hydrogen, and oxygen in this chemical reaction. We have 2 carbons on the left-hand side, 1 carbon on the right-hand side. We have 6 hydrogens on the left-hand side, 2 hydrogens on the right-hand side. We have 2 oxygens on the left-hand side and 1 oxygen, on the right-hand side. Now, if we look at step 2, it says determine which atoms are unbalanced. Well, all of them are unbalanced. Step 3 says to balance the chemical reactions, or balance the atoms one at a time using the coefficients. The second sentence to step 3 applies to this example. Start with atoms that appear only once. So that means that looking at oxygen, we can see that oxygen appears twice on the product side in both of the molecules, and then also again on this side, on the left-hand side. So changing any one of those 3 coefficients would change the number of oxygen atoms. So we're not going to worry about the oxygens until the very end. All right, let's change the carbon. We have 2 carbon atoms on the left-hand side, so let's change this coefficient to a 2. Now we have 2 carbon atoms on the right-hand side. Of course, we have changed our number of oxygens, but we won't worry about that because we will change them again before we get to the chance to balance the oxygen atoms. Now if we look at our hydrogens, we have a total of 6 hydrogens on the left-hand side, so let's put a 3 here so that we have 3 times 2, or 6 hydrogens on the right-hand side. Now, carbon and hydrogen is balanced. Let's go ahead and count up all the oxygen atoms we now have on the right-hand side. From carbon dioxide, we have 2 times 2. We have 4 oxygen atoms from carbon dioxide. We have 3 water molecules, therefore we have 3 more oxygen atoms on the right-hand side. We have a total of 7 oxygen atoms on the right-hand side. This poses a problem, as on the left-hand side, oxygen must come in a ratio of 2. It must always be an even number. we cannot just change the water molecule coefficient to a 4 because then our hydrogen would be unbalanced. We would have 8 hydrogens, and that would be tricky to then try to balance with the 6 hydrogens on the left-hand side. So what we do in this situation is double all of the coefficients so that we can change the number of oxygen atoms on the right-hand side to an even number. So we're going to change this to a 2, and then we're going to change this to a 4, and this to a 6. Again, we're leaving our oxygen right here blank because we're going to recount our atoms of oxygen. We now have, from carbon dioxide, 4 carbon dioxide molecules, each one having 2 oxygen atoms. 4 times 2 is 8 oxygen atoms from carbon dioxide. We have 6 water molecules, therefore we have 6 more oxygen atoms. This gives us a total of 14 oxygen atoms, which should be expected since we doubled the amount of atoms that we had. Now, if we were to change this coefficient to a 7, we have 7 times 2, 14 oxygen atoms on each side. Let's recount our carbon and hydrogen just to make sure. We have 2 times 2 on the left-hand side, so we have 4. We have 4 carbon dioxide molecules, each with an oxygen, or each with 1 carbon atom. And then we have 2 times 6 hydrogen atoms on the left-hand side, and then 6 times 2 hydrogen atoms on the right-hand side. And now everything is balanced in this chemical reaction.